So this is something I started in class on Tuesday, I believe, about the calculating the moment of inertia of a rigid body, and I'm just going to kind of go over that again because I didn't quite get finished, and then probably extend it a little bit further in maybe a second video. So if we want to calculate the moment of inertia of a rigid body here, we're just using a rod that we want to know its center, moment of inertia rather, about some axis here, about the y-axis. We can call this the y-axis. This might be positive x. It has a rod of some length. Let's call that length L. The whole key in determining this, right, we use the expression really isn't all that complicated. The moment of inertia is the integral of r dm. Oops, it's not a subscript. dm. Where dm is some differential piece of mass out of this entire rod. So we can think about that if this was maybe a long, conceptually think of this rod as a long line of maybe dimes or a very small coin. So it has, you can think of the mass of that little tiny piece of stuff inside the rod as being some differential mass. In this situation, because of the symmetry here, we can actually consider this little piece of dm, this differential piece of mass, is related to, has a little tiny width, and we might call that width, that this differential mass is somehow proportional. This isn't an alpha sign, this is a proportional sign to the differential width that this little slice has. So this has a little tiny width associated with it. I'm not sure how clearly you can see that. Maybe I'm not drawing quite large enough. But this has a differential width. My pen appears to be dying. Oh, there it goes. It has a differential width of dx. And we can relate these two quantities by calculating the linear mass density. So just like you would calculate normal density would be mass over volume, right? A volume mass density. But a linear mass density is simply a mass over some linear distance. So here we have this differential chunk of mass depends on the differential width of this little, those two have a specific ratio that's equal to some linear mass density. And that density isn't just true for this piece, because if we consider something that has uniform density all the way through it, it not only does this lambda equal the linear mass density of the ratio of these two things, it's also equal to the ratio of the entire mass of the whole rod divided by the entire rod's length. Right? And that makes sense, that the ratio of these two things would be in proportion to the ratio of these two quantities, because really it's simply the ratio of these two things is the same as this. It's just that you sum up all of these different pieces, right? So it's the ratio of those two things that are equal to one another. So when we go to start plugging this into our expression, we can find the moment of inertia as being the integral of r, which r in this situation is only in the x direction, right? So we have a value of x times dm, which dm we can write as lambda dx, right? So I'll be multiplying dx here, and then evaluating the next step, lambda is also equal to mass over length. It's mass divided by length. I've already made a mistake. All the way back up here, this isn't r dm, this is r squared dm, right? That should be a square. So that comes down here, this is actually x squared. I knew something looked screwy. So this is x squared, right? So substituting mass over the entire mass of the rod over the length of the rod in for lambda times that dx, and integrating from the limits of integration here. We're going to start at the 0 point, x equals 0, all the way out to x equals L. So 0 to L. All right? So now we evaluate that, we pull our mass and our length out in front, and we're simply integrating from 0 to L x squared dx. And that's going to equal mass over length times 1/3 x to the third, evaluated from 0 to L, which is going to equal m divided by L times 1/3 times L to the third power. Right? We also minus 0 to the third power if we want to be explicit. We can say 0 to the third power, that's the lower limit, that's just 0. So when we multiply our L's through, we get the center of mass of a rod about an endpoint as being 1/3 mass times the length squared. Alright? Fantastic. So next we're going to actually look at the moment of inertia of a rod about its center point. And we'll do that in the next video.